Okay, dear students, today let's discuss the physics behind the laser because in your present course of material science there is a topic related to lasers. So I have made effort to clear that topic in depth. So the topic of the day will be physics behind the laser. Okay. So, what the definition of laser? Laser is a device that generates light by process called stimulated emission. That is, laser stands for light amplification by stimulated emission of radiation, right? So there are semiconducting lasers are multi-layer semiconductor devices that generates a coherent beam of monochromatic light by laser action. And a coherent beam resulted which all of the photons are in phase. So dear students, I want to make a clear concept related to laser. We are studying here that stimulated emission. Okay, let's try to understand this first of all. Yes, now see, if I have to differentiate between the laser light versus ordinary light, then we will see in the diagram that this is a ordinary light torch, and it emits light that is multi-directional, composed of many different wavelengths, right? And these emitted waves, they are not in phase with each other. But as we see on this side of laser, and the light is unidirectional and composed of single wavelength. That's the beauty that we have gained the output like a highly coherent beam from the laser. What, why, and how this laser works, that's very important to understand. Okay, the next slide. Now see, this is the general differentiation between the ordinary light source and the laser source. The number one point is light emitted is not monochromatic in ordinary light source, just like your bulb. And on the laser side, light emitted is highly monochromatic. First, the property of the laser, that is highly monochromatic light waves. Second one, light emitted does not have high degree of coherence in ordinary light source. But in a lasers, when we are using the laser as a source, it has high degree of coherence, highly coherent beam. Number third point, emits light, ordinary source emits light in all direction, that is multi-directional waves, emitted waves are there, which surrounds your ordinary light source like electricity bulb. Normal light waves we are observing in this source bulb, that different wavelength, different frequency we are getting from the ordinary source of light. But okay, so but the laser source light only in one direction, unidirectional and highly directional. In next slide, I present some few mathematics and physics in all these statements. And number fourth one, light, in ordinary light source, the light is less intense and less bright. But in case of laser light, it is much intense and highly bright, high intensity. So, if we are observing the sunlight, there is a multiple frequencies of light waves, and they are all non coherent. If we are using the incandescent valve, just ordinary valve, then we have the single frequency, but the light waves are non coherent. Okay, so if we are in the laser light, then we can check that all the light waves, they are in phase with each other. They superimpose with one wave on the another to make a resultant wave highly intense. So these are the basic differences between ordinary light source and the laser light source. Okay, so if I want to move further, then in introduction part, actually the whole theory that is of the related to stimulated emission of radiation, that is framed by a well-known scientist Einstein in 1916. He concluded that he observed that electromagnetic radiations can interact with matter through following three processes. First process, that is stimulated absorption. The second is spontaneous emission, and third one is stimulated emission of radiation. And this stimulated emission of radiation, that is the basic principle on which your laser action takes place. Okay, let's understand one by one. Okay, in this figure we are observing that there is a photon that is uh, moving towards a system, any type of system. And if the system atom of the system, they are in ground state, lower level, then this atom, this photon that will observe by the atom having frequency h nu greater than the band gap. Yes, that the case of semiconductor lasers, but here I am saying in linear way, that photon that observed by the atom, and after that this atom goes to the upper level of energy, that is excited states. Okay, and yes, this absorption of the photon by the ground state atom is known as stimulated absorption. Second, okay, and the lifetime of this excited state, that is generally it is 10 raised to power minus 8 second. Now your atom that is now in the excited state, but after uh, because the lifetime 10 minus 8 second, and a number of atoms are also present in the excited state, they try to collide with each other and lose energy, and again the atom that is absorbed in the previous state, now that again lose energy and goes to the ground state by emitting the observed photon in the previous level. And this phenomena is your spontaneous emission. I am using here word spontaneous because it is just emission within 10 minus 8 second. Very fast, spontaneous. Now, this is third one. Okay, stimulated emission. Now what is there? Now if I suppose the second state after absorption, your atom that is in E2 state, excited state. Now what you do when the atom is in excited state after observing the primary photon, and you at that state again add a more photon externally to the system, then what happens? This excited state, that that becomes the metastable, and your atom goes to another higher one state, and higher one, that is E3. I'm going to mention in the next slide then your E3 becomes the excited state and E2 becomes the metastable state, and the lifetime of this metastable state, that is 10 raised to power minus 3 second, which is much more greater than 10 minus 8 second lifetime of the spontaneous emission. Now in the next slide, now say before, yes, we can recapitulate our concept here. Before absorption, your this is your atom in the ground state, and there is a photon that is coming towards the system from external agencies. And after that, what happened? Yes, this atom observe the photon and goes to your next higher state, excited state, E2. This is this the whole process is your stimulated absorption. And after that, yes, E2, and it is a very quick phenomena because 10 minus 8 second lifetime of this state, again your excited atom that lose energy, and the loss of energy that equal to the energy absorbed in the previous state. सो द फोटोन, जो फोटोन आपने लिया था, ऑब्जर्व किया था, उसको रिलीज कर दिया, एंड नाउ अगेन योर एटम इन द ग्राउंड स्टेट इज द स्पॉन्टेनियस एमिशन. नाउ in stimulated emission, if your atom that is, yes, that is in this state E2 like this, and you again at this state, क्योंकि इसने पहले एक फोटोन, प्राइमरी फोटोन पहले ऑब्जर्व कर लिया था, now you again give the next photon to it. Now what happened? Now the energy level of this atom again increases to another higher excited state, and there is and after that, this is the metastable and higher excited state, and your the first, the excited one state, that has now two atoms, two photons, atoms observe two photons. Now again it is a very spontaneous emission takes place there, because 10 minus 8 second lifetime, and it then when it release, when it lose its energy due to atomic collisions, again you get, now you get the two photons, one primary, second secondary, and these two photons are in phase with each other, hence the phenomena of stimulated emission occurs. So this is the basic difference between spontaneous and stimulated emission of radiation, right? In other way, I have represented these two phenomena like this. One more thing. Generally, number of atoms in ground state, they are more than the number of atoms in the excited state, and this is the case for your absorption and spontaneous emission. But when you are in stimulated emission, you have different phenomena, because there is ground state E0 is there, E1 becomes the metastable, and E2 is your upper excited state, and in that particular situation, the number of atoms in the excited states, they becomes more than the number of atoms in the ground state, and this particular situation is known as population inversion state. And once the population inversion is there, the stimulated emission of radiation starts, or in the particular, in nutshell we can say, there is laser excitation starts. Okay, so these are the basic differences between the three types of emissions and absorption, and this is the interaction of electromagnetic waves with matter, right? Three processes are these. Okay, now if mathematically, yes, if mathematically I have to understand that what the physics in these processes, then let's start first. Stimulated absorption of radiation. Let E nu be the energy of the incident radiation, and the rate of stimulated or induced absorption is directly proportional to I am writing that E nu be the energy of the incident radiation. जो इंसिडेंट हो रहा है फोटोन उसकी एनर्जी क्या है E nu, and the rate of stimulated or induced absorption is given by, I am writing that RSTA, stimulated absorption. A stands for absorption, is directly proportional to number 1, N1, number of atoms in the ground state 1. And this rate of stimulated absorption is directly proportional to your energy density, energy of the incident radiations. कितने एटम है और कितने फोटोन आए दोनों के ऊपर डिपेंड कर रहा है. Then collectively I can write RSTA directly proportional to N1 E nu, and which implies RSTA equal to V12. V12, it is a proportionality constant and very important coefficient, Einstein coefficient. In Einstein coefficient 1 2 stands for आपका जो एटम है वन स्टेट से सेकंड स्टेट में गया है, 1 stands for your ground state and 2 stands for excited, N1 E nu. So this is equation number 1, that RSTA equal to B12 N1 E nu, where V12 is coefficient of proportionality and it is called Einstein coefficient for stimulated absorption from energy level 1 to energy level 2, as we are observing it in the figure here. This is N1 number of atoms. I have made the atoms. This is the E1 ground state, E2 excited state, and the rate कितना इसमें फ्लो हो रहा है एटम्स का फ्रॉम ग्राउंड टू आई, ग्राउंड टू एक्साइटेड स्टेट. we can represent that rate by equation number 1. Okay, now the second, yes, this is the figure that you have to understand. I just starting this portion of the figure now. Now spontaneous emission, second process, the rate of spontaneous emission, this side, this side, this side, okay, that is directly proportional to N2, because you have the same atom here, you have the same atom, and the energy that is observed by this atom, that is photon, that is within this atom here. So simply here the rate of SPE, spontaneous emission, directly proportional to N2, the number of atoms in the excited states, and I can, which implies RSP equal to A21 N2, and A21 again directly proportionality constant hai, and it is called Einstein coefficient for spontaneous emission of radiation from level 2 to 1. I am representing it 2 to 1. So A21, and yes, we have a stimulated absorption, stimulated emission. उनके लिए मैंने कोफिशिएंट बी लिया है, लेकिन जो स्पॉन्टेनियस है उसके लिए मैंने कोफिशिएंट ए लिया है. It is 2 to 1, equation number 2. This is the case here. And in general, yes, here the N1 is greater than N2 till this situation. N1 is greater than N2. We are observing that N1, these N1 number of atoms in the ground state, they are more than that number of atoms at that state. Up to this situation, we have the two processes. Now move further. Okay, this is again that figure. Now stimulated emission of radiation. The rate of stimulated emission of radiation, that is given by RSTE, stimulated emission, it is directly proportional to N2 and also directly proportional to E nu, because you have also provided external photon at that particular situation. So RST directly proportional to N2 and also it is directly proportional to E nu. So in totality, RSTE, rate of stimulated emission, directly proportional to N2 E nu, and which implies RST equal to B21. Then in the first step we have V12 but I am writing here B21 N2 E nu, where V21 is the coefficient of proportionality and it is called the Einstein coefficient for stimulated emission of radiation from the level 2 to level 1. Equation number 3. Mathematically, first of all, we observe physically and then mathematically the situation like this. Now, yes, now here, this is the scenario that is drastically changed here in this step. Previously, we have N1 is greater than N2, but you are now in the stimulated emission of radiation stage. The number of atoms in the ground state, they becomes less than the number of atoms at the higher state. So I am writing here N2 greater than N1. It means this particular situation, when number of atoms at higher states, they becomes they becomes more than that of number of atoms in the lower state. This particular state is known as population inversion state. You have here N2 greater than N1. So this is after that what happened, because your system now this excited state that becomes now metastable, it is not excited now, and because number of more few atoms again goes to the higher states. Now higher state another one, and this is the metastable. Okay, in the yes. So what happened now? If I want to find the physics here, that at thermodynamical equilibrium we have RSTA, that is stimulated absorption, जहाँ से ये प्रोसेस शुरू हुआ, that is equal to RSPE plus RSTE, rate of spontaneous emission and the rate of stimulated emission. Rate of stimulated absorption that equal to the 2. Yes, it's a natural equation, and on putting the values of the three rates, what we get, V12 N1 E nu, and we just putting all the values, and जो E nu वाले थे मैंने वन साइड ले गया उनको, एंड E nu वाले थे आपके पास what B12 N1, और यहाँ था आपके पास B21 N2. ठीक है, यहाँ से इसको आप ले गए हैं वहाँ, और यहाँ आपके पास वही रहा है स्टेप में. अब B12 N1 B21 N2, और इन द नेट सेल आगे क्या मिल रहा है आपको, आपने ये पहली टर्म को जो है दूसरी टर्म को कांस्टेंट ले लिया, बिकॉज मैंने N2 से N2 जो N2 ये जो है दीज आर स्केलर क्वांटिटीज, सो मैंने इनको ये करना है, सो आई टेक दिस कॉमन and the situation like this, and now your energy of the incident radiation that we can find by this relation A21 divided by B21, and the situation is like this. N2 से N2 भी हमने cancel out कर दिया है. ठीक है. Now because we all are working on quantum system, so I have to use here some quantum phenomena. So according to Maxwell-Boltzmann distribution, it is a classical physics, but in a certain limit. Okay, according to Maxwell-Boltzmann distribution law, ये कहाँ से आता है लॉ हमें पता है. When there is distinguishable particles are there and you have to count them, you have to use the statistical data analysis there, and so from there we have studied about in first year in the statistical physics this law, that Maxwell-Boltzmann distribution law क्या बोला है हमें, N1 by N2, that yes, actually what is this, n exponential E upon kBT, that is directly proportional to the number of atoms. Actually this is the basic formula, that is number of atoms can be represented by exponential term having energy and temperature as a factor. So I am using for N1 I am writing exponential minus E1 upon kT. For N2 I am writing exponential minus E2 upon kBT, and and this is n1 by n2, and ये E2 जो है ऊपर चला गया, then you have E2 minus E1, and this is the energy difference, and energy difference between the two states or two bands, generally that is h nu. So in the next step, n1 by n2, that is exponential h nu by kBt. This is the in accordance with the Maxwell-Boltzmann distribution law. Now on putting this value here, I am just want to put this value. This is A21 B21 आपने यहाँ लिख दिया है, and yes, there is n1 by n2 is there, n1 n2 I put value here. In this step we have put this value here. ये देखिए जरा, मैंने इस वैल्यू को पुट कर दिया है. नाउ दिस इज द अगेन another relation for energy of the incident photon that is observed by the initial atom at ground state. Okay, but according to Planck's radiation law, because we are dealing with the radiation, so these are some basic laws, fundamental laws related to radiation, that according to Planck's, the energy density always equal to energy density of emission of any type of photons, whatever it is X-ray photon, whatever it is light photons, that is 8 pi h nu 3 c3 1 upon exponential h nu kBt minus 1. And simply I am writing it just E nu equal to 8 pi h nu 3 c3 1. I just put here 1 into this. Now comparing this equation with the previous one, comparing this is the our first equation, and this is our second equation. On comparing, what we are getting, that this first term A21 by B21, that equal to what, this term 8 by h mu 3 by c3, and this is the first Einstein relation for stimulated emission of radiation. And second one in the previous equation we have V12 by B21, and what is the value, that is equal to 1 on comparing. So B12 to B21, that always equal to 1, and yes, it means both are equal. This is the second Einstein relation. So this is the pure physics behind the stimulated absorption, spontaneous emission, and stimulated emission of radiation, that all the students should know about this basic fundamentals. Okay, now move to the next point of the topic, properties of laser. Laser has generally four properties, and they are quite different from the ordinary source of light. First is high directionality, second is high intensity, third one is extraordinary monochromaticity, and fourth one is high degree of coherence. Okay, the sodium lamp is coherent, sodium light is coherent, but it is not highly coherent. Generally, sodium lamp has two wavelengths, 6596 and 6590. But generally, we can say the sodium light is a coherent source of light, but we cannot say it is highly coherent. Our laser light is highly coherent. And okay, let's see the physics behind these four properties. This is very, very important to understand, my dear students. Okay, high directionality. Okay, an ordinary source of light emits lights in all possible directions. We have already discussed this. On the other hand, a laser source emits radiation only in one direction, and laser light is highly directional. Okay, if I understand this, when a light beam of wavelength lambda, it comes out of an aperture of diameter d, from figure, this is the aperture diameter d, then the beam propagates as a parallel beam through a certain distance. Then after traversing few distance, the beam, it travel a few distance, parallel distance, that this particular distance is known as Rayleigh range, and yes, and after this particular distance, now your beam get diverges. Okay, and this length is, yes, I am saying in the, yes, this is the r with the radius of this final cone, that is geometrically we have made here. So This relay range is given by this relation d square y lambda. D, that is the square of the aperture size to the wavelength of the light that is emitted by the laser. So this is known as Rayleigh range. I am giving question number 1. Beyond this range of distance, the beam of light begins to diverge due to diffraction effects, and the angular spread of the beam is given by this relation, this theta, that is the angular spread, that is equal to beta lambda y d. Here d is in optics we have d. This is the distance between the two coherent sources, and capital D will the distance between the coherent sources and the screen. But here what the d representing the aperture size. Okay, and beta represent the proportionally constant, and for if you are working in air medium, then beta that you have to take it equal to 1. Equation number 2. These are two relations related to the basic of as we are directional T. Now in the third step, if I have a question that why how these relations confirm that high directionality, I have made an example here. Let lambda be the 5000 angstrom. Okay, I'm writing 5000 10 minus 10 meter. D, the size of aperture, that is I am taking it 0.02 meter. Beta equal to 1 if the air is the medium. So what the angular spread, आपकी laser light spread कितनी होगी, that is beta lambda by d. So if you put all the values here, then finally now if you I am writing here, I am converting step by step, then theta that equal to 2.5 10 minus 5, and if you convert it into radian, then it is 0.01 milliradian. 0.01 milliradian. So this is the too less value as compared to the value of your ordinary source of light. So we can say that 0.01 milliradian represent the conclude that laser light have highly directionality. First property. Second, high intensity. Okay. So the intensity of light at any point is the amount of energy passing normally per unit area per second at the point. Because of the small divergence of laser beam, the intensity is very high, and it can be focused to extremely small division. Even 1 watt of laser beam is 1000 times more intense than 100 watt lamp. देखिए जरा, ये 1000 times more intense than 100 watt bulb in your room in the house. Okay, so how we can say that these are highly intense? This is just a statement. Now how I can prove it? Yes, let f be the length, a be the radius of the lens used to focus the light beam, then the radius of the spot at which light can be focused, that is given by this relation. Yes, this is the light, and yes, this is a lens having radius a, then what the spot radius? So spot radius will be r equal to f lambda by a. Equation number 3. This is the way we can calculate the radius of the spot. Okay, सर मैं लेक्चर में हूँ थोड़ा सा, नहीं. ओके सर, ओके, ठीक है. So this is our relation, and yes, we can compare this radius of the spot for laser as well as for ordinary light source. Let lambda, that is 6000 10 minus, okay, your f equal to 10 centimeter, generally we have take this, and a equal to 10 centimeter, then area of the spot, generally we are taking the 6000 angstrom wavelength, that is pi r square, and when we put all the values r, this is the radius spot here, then it is 22 by 7, 6000, 10 minus 8 centimeter, 10 centimeter, 10 centimeter. Then finally what we have, the area of spot, it is 113.04, 10 minus 10 centimeter square. Okay, now apply for laser. The area of spot is this. Okay, we have calculated the previous step. Now, intensity of 1 watt laser, intensity, that is power upon area, 1 watt by area. So 1 upon this, then this intensity, that approximately equal to 10 raised to power 8 watt per centimeter square. That is very high value we are getting. But if I using this the same process for 100 watt lamp, it will be, area of the spot will be 4 pi r square. And this is for the bulb we are using in our houses, our homes. 4 into 22 by 7 into 10 centimeter square, and then the intensity P upon A, 100 watt by this, the term will come, it is intensity will be 0.08 watt per centimeter square. And we can compare the two values. One side we are 10 raised to our 8 watt, and one side we have 0.08 watt, that is very low value. So we can say that the laser beams are highly intense. Okay, now third is high monochromaticity. The light emitted by laser is highly monochromatic. Laser emits light beam of particular wavelength and particular frequency, and laser has very small frequency spread, that is del nu. And if let the spectral line emitted by the light source is nu naught, जो लाइट सोर्स है उसका जो इनिशियल जो हमारे पास फ्रिक्वेंसी है उस लाइट की, आई जस्ट टेक द न्यू नॉट, देन द क्वांटिटी, दैट frequency spread, that is change in the frequency after traveling few distance, divided by nu naught, represent the degree of monochromaticity of the light beam. The monochromaticity higher for the value of high, yes, अगर अगर मेरे पास del nu by del, yes, yes, I am writing some okay, sorry, del nu by nu not directly proportional to 1 upon monochromaticity, that is monochromaticity is inversely proportional to this term del nu by nu naught. Laser light has smaller frequency spread, it is about 500 hertz, whereas ordinary light has high frequency spread, it is 10 is to 14 hertz. कितना spread होता है आपका laser, it is what the frequency at that time, that is 500 hertz, whereas the ordinary light has higher frequency spread, it is 10 is to 14 hertz. Okay, so if I want to calculate the monochromaticity, then what I have to do? We have given that nu naught, that is 5 into 10 to 14 hertz with the frequency of spectral line emitted light source. Okay, for ordinary light we have nu naught equal to this, nu naught equal to 5 to 10 14 hertz. Okay, del nu spread frequency set, that is 10 is to 10 hertz. Now the term del nu by nu naught, that comes to be 2 into 10 minus 5. Okay, that is हायर वैल्यू मैंने किसके कंपैरिजन में लिखा, यहाँ देखेंगे, अगर if I have the laser, then this term becomes to be, because 500 frequency spread is there for laser, 10 minus 12, and there is 2 into 10 minus, this is the higher value of this term, this is the lower value of this term, and reverse the case for degree of monochromaticity. For ordinary light we have low degree of monochromaticity, for lasers we have high degree of monochromaticity. Hence we can also prove our third statement that laser light are highly monochromatic. Okay, so this we can see that this is the second color represent your ordinary light, but the sharp peak representing your laser light beam in the graph. Okay, now fourth one, because my topic that I want to further for our the topic that relates in your syllabus, but these are few very important fundamental related to lasers that I'm explaining before that topic. Okay, now fourth property, high coherency. The light source which emit light waves of same frequency, same wavelength, and having same phase, they are coherent source of light, as we know about this. And the phenomena is called coherent laser light, and yes, and has high degree of coherence. We are making a statement. The other properties of the laser light, for example, directionality, intensity, monochromaticity, are in a way or other, they are related with coherent property of laser light. So laser light is coherent because it is emitted by the stimulated emission of radiation, while light from ordinary source, it is incoherent because it is emitted by spontaneous emission of radiation. Okay, so this we have explained this. So these are uh, for coherency we have to go for to the inherent phenomena for coherence, that its types. There are two types, temporal coherent and spatial coherence. Because coherency that need to be explained, the important property of the lasers. Okay. So first one is a temporal. A plane wave, yes, this is just example. A plane wave coming from the light source can represent it graphically by this. Yes, this is sinusoidal. This is the cosine wave. This is sinusoidal wave. We can represent by making the two. This is the cos wave. This is cosine wave is there. This is the sine wave is there. Okay, we can represent any signal by this. Okay, now yes, temporal coherence, it is not true, but अगर हम ऐसा बोले कि कोई भी लाइट वेव है, कोई भी वेव है वो इसी तरह से चलेगी, ऐसा नहीं है. सो आई एम राइटिंग हियर, इट इज नॉट अ ट्रू रिप्रेजेंटेशन ऑफ आइडल प्लेन which is coming from the actual source, like just like a sodium lamp. In actual practice, the waves given out by an actual source represented by this way. Yes, there is with this some for some time we are observing that there is a coherency up to this point, and there is after some time the two waves, they are incoherent. So this is the actual representation of the light beam or any type of sound beam कोई भी है. So coherency is for some time, then incoherency, then coherency, then incoherency, and same way. So I am writing here one thing. As we see from figure that in case of actual source, the waves have definite phase relationship only for limited time. That is, yes, जहां तक कोहरेंसी है कितने टाइम तक के लिए, मैं उस टाइम को बोलूंगा कोहरेंट टाइम. इट इज रिप्रेजेंटेड बाय टीसी, टॉसी. During this time period tau c, the light wave distance L, that is coherent length. L represent the coherent length. जब तक आपकी लाइट वेव्स आपस में सुपरपोज करके इन फेज में है, कितनी देर तक के है, दैट इज टी सी. कितने कितना डिस्टेंस तय कर लिया, दैट इज कोहेरेंट लेंथ. ओके, फॉर ऑर्डिनरी लाइट वी हैव टी सी इक्वल टू 10 - 10 सेकेंड. So the coherent length we can calculate that C cross TC. So this is a simple formula, distance equal to velocity into time, L equal to this into this. So the L equal to 3 into ये कितना बच गया -2 मीटर, that is 3 सेंटीमीटर, that is small value. Ordinary light का जो coherent length है, कितनी देर तक वो light waves absorb, that is 3 centimeter. But for laser light we have TC, that is 10 - 3 second, and it is 3 into 10 is 8 meter per second, 10 - 3 second. Okay, that is 3 into 10 5 meter. L equal to 3000 kilometer, last value. This is why the laser light can be used to calculate the distance between moon and earth. 3,84,000 kilometer is the distance between the two. So laser lights can easily determine the distance between the earth and the moon, because coherent length for laser, that is 3000 kilometer. Okay, So second was spatial. मैं just I just okay. The spatial coherence. Over what area does the light remains in phase? That's all. In temporal, we are just observing the length, but in spatial, we just observing the area, or over what area does the light remains constant, light remains in phase. Okay, so this is spatial coherence. So by making use of this numerical concept, we can say that the laser lights are highly coherent. So my dear friends, till this we have studied the laser light important properties, and before that how the stimulated emission of radiation help to create the population state and to achieve the laser action. Okay, so in the okay, now what are the components of laser? आपने थ्योरी पढ़ लिया, आपने फिजिक्स पढ़ लिया, लेकिन आप प्रैक्टिकली टेक्नोलॉजिकली आप लेजर को कैसे बनाएंगे? तो लेजर बनाने के लिए मेरे पास तीन कंपोनेंट की जरूरत पड़ेगी. पहला आपका एक्टिव मीडियम, सेकंड इज योर पंपिंग सोर्स, एंड थर्ड इज योर रेजोनेंट कैविटी, और ऑप्टिकल रेजोनेटर भी इसे बोलेंगे. चलो देखते हैं जरा ये कैसे काम करते हैं. तीन. अब now I come from science to technology. The next part related to technology. Okay, so yes, now see here. The first part we are saying that active medium. Okay, yes, ये this portion, ये आपके पास ऐसा पोर्शन चाहिए मेरे को लेजर लेजिंग सिस्टम के लिए कि ये एक एक्टिव सोर्स की तरह काम करे. आगे देखेंगे हम कैसे करेंगे. ठीक है. देन सेकंड पोर्शन इज व्हाट? सेकंड पोर्शन इज पंपिंग सोर्स. ओके, ये जो आपने पंपिंग करना है, पंपिंग. ओके, लेट्स स्टडी वन एक्टिव मीडियम. यस, ओके. For example, we have the solid state laser. Okay, solid state laser, that is generally we are saying that ruby rod, ruby laser. So ruby, it is, ये जो रूबी है आपके पास, ये क्या है? ये एल्युमिनियम ट्राइऑक्साइड का क्रोमियम के साथ मिक्सचर है. दैट इज द एक्टिव मीडियम. दैट इज द एक्टिव मीडियम. अगर मेरे पास कोई गैसियस लेजर ऐसे हीलियम नियोन है, तो हीलियम और नियोन क्या है? गैसेस है, मिक्सचर ऑफ He and Na. These are the active medium. If I have semiconductors, then what I have the active medium? Gallium arsenide. These two different elements mixture is the active medium. इसको हम गेन मीडियम कई बार बोलते हैं. Generally, in an active medium, the number of electrons in the ground state greater than excited state. Okay, we all have studied this. So the first component that any laser system was, that is the active medium. Okay. The second portion of optical medium. एक ऐसा सिस्टम जिससे the process, now see, the process in which population inversion is achieved in a laser system is called pumping. Population inversion state क्या है? As we have clear that N2 नंबर जनरली होता क्या है, आपके जो ग्राउंड स्टेट एटम्स है वो कम है एज कंपेयर टू द number of atoms at the excited state, generally for ordinary source of light. But laser में हम उल्टा कर देते हैं, because we just pump the system, we give some few external photons, and then there is a population inversion state is achieved. So ऑप्टिकल मीडियम क्या करेगा? उस पॉपुलेशन इन्वर्स स्टेट को तैयार करेगा ताकि लेजिंग एक्शन हो. अदरवाइज वो स्पॉन्टेनियस एमिशन होगा और लाइट की तरह लाइट देगा ये. ओके, सो हम यहाँ ये भी पता है. हम आगे देखते हैं जरा रूबी लेजर में और हीलियम नियोन या सेमीकंडक्टिंग लेजर में आप कौन कौन से ऑप्टिकल मीडियम यूज करेंगे, हम इसको स्टडी करेंगे. नाउ थर्ड कंपोनेंट, रेजोनेंट कैविटी. यस, रेजोनेंट कैविटी ये तीसरा कंपोनेंट है. यस, अब ये भी क्या रहेगा, एक मिरर रहेगा, ये भी एक मिरर रहेगा, ये हाईली रिफ्लेक्टिंग मिरर होगा, ये ये आपके पास पार्शियल रिफ्लेक्टिंग होगा, पार्शियली बोला है वैसे, ये अगर 100% रिफ्लेक्टिंग है तो 90% रहता है, इससे ज़्यादा 98, 90 to 98% लाइक दिस। तो ये जो कंपोनेंट होगा, दैट इज दिस इज नोन एज द ऑप्टिकल रेजोनेटर। This is the third component we need to make the we need to fabricate the lasing system. Okay, and it is the key component. It guides the process of stimulated emission. It consists of pair of mirrors, out of which 100% reflecting and 98% reflecting mirrors are there. The active medium is placed in between these two mirrors. Mirror 2 is called output coupler as it allows some of the light photons to leave the cavity to produce laser output beam. Light reflects from this mirror and thus pass through an active medium many hundred of times before executing the cavity. ये मिरर, ये जितने भी आपकी लाइट्स बीम रिफ्लेक्ट्स करेगा, पता नहीं कितनी बार करेगा, उसके बाद बहुत बार रिफ्लेक्शन के बाद ये इसको एग्जीक्यूट करेगा। Okay, and many optical devices such as spinning mirror, filters, absorbers may be placed within the optical resonator to produce variety of effects on the laser's output, such as production of pulse laser output. So these three are the basic components for the laser: active medium, pumping source, and resonant cavity. Okay, so okay, so now I want to start your first topic, that is solid state laser. Solid state laser, it is its a second name is ruby laser. It is discovered by T. Mayman in 1960. The output of this laser is pulsed. It not produce the continuous one. Pulse mode, रुक रुक के हमें आउटपुट मिलती है। ऑप्टिक जो ऑप्टिकल पंपिंग है, दैट इज दिस मेथड इज यूज टू गेट द पॉपुलेशन इन्वर्जन स्टेट। और ये 3 लेवल लेजर सिस्टम है। इसके कंपोनेंट्स क्या है? एक्टिव मीडियम किससे बना है? एल्यूमिनियम ट्राइऑक्साइड एंड क्रोमियम ऑक्साइड ट्राइऑक्साइड, जिसमें 0.05% आयन जो है एल्यूमिनियम आर रिप्लेस्ड बाय द क्रोमियम आयंस। 0.05, जैसे हम डॉपिंग करते थे पीएन एनपीएन जंक्शन में एन टाइप में, वैसे ही मतलब आपने क्रोमियम की डॉपिंग करनी है एल्यूमिनियम की, और जो उसका जो रॉड है दैट इज रूबी रॉड, ठीक है। रेजोनेटर कैविटी, मिरर M1 M2, ऑप्टिकल पंपिंग एंड यस ये जो पंपिंग सिस्टम है यहाँ जीनोन फ्लैश लैंप, अभी बताएंगे हम इसको। यस ये जो हेलिकल आपके पास क्या है, जीनोन फ्लैश लैंप की ये हेलिकल ये रॉड भी इसके साथ है जो पंपिंग के लिए यूज की जा रही है। हाईली इंटेंसिफाइड फ्लैश पंप इज देयर। ये क्या होगा, आप ये पावर सप्लाई देंगे, इससे ये रॉड जो है गर्म होगी और इतनी टेंस हो जाएगी कि ये जो इसके बीच में जो आपने एक मटेरियल रखा है जिसे हम रूबी रॉड बोलते हैं, ये जो कि एल्यूमिनियम और क्रोमियम का है, इसको हीटअप करना है। और जैसे यस, और ये रॉड के ये लेंसेज है दो। ये जो पहला लेंस है इसका एक साइड वन एंड 100% रिफ्रैक्टिव मिरर इज देयर एंड 95% इज इन द सेकंड, 98 तक हो जाता है ये। एंड जैसे ही आपका ये सिस्टम चलेगा, यहाँ से आपको लेजर बीम मिलना शुरू हो जाएंगे। दिस इज द बेसिक स्ट्रक्चर फॉर रूबी रॉड लेजर। ओके, वी कैन यस, इसका डिसएडवांटेज बी द आउटपुट पल्स्ड आउटपुट नॉट कंटिन्यूस एंड हॉट एंड कूलिंग रेज रिक्वायर्ड। यस, बिकॉज जब आपने इसको हाईली टेम्परेचर से कर दिया तो इस सिस्टम को कूल करने के लिए हमें कूलिंग सिस्टम की ज़रूरत पड़ती है। और ये क्रिस्टल सॉलिड स्टेट है तो इसमें कई बार ये जो आपके क्रिस्टल है, रूबी क्रिस्टल जो है, इसमें कई बार डिफेक्ट्स और इम्परफेक्शन हो जाते हैं, तो आपकी आउटपुट जो है ठीक ढंग से नहीं मिलती है। तो दिस इज योर फर्स्ट सॉलिड स्टेट लेज़र, इसे हम रूबी लेज़र बोलते हैं। यस, ये दिस इज द सेकंड एनर्जी बैंड डायग्राम फॉर द सेम। यस, हम यहाँ से देख रहे हैं, ये आपका इंसिडेंट फोटोन है, कितने का दिया आपने, 55500 एंगस्ट्रॉम की वेवलेंथ का दिया है। ठीक है, पंपिंग की ऐसे ऑप्टिकल पंपिंग बाय जीनोन फ्लैश लैंप। अब आपके एटम्स जो है वो हायर स्टेट को चले गए, E3 शॉर्ट लिव स्टेट है बिकॉज 10-8 सेकेंड इसका लाइफ टाइम पीरियड है। तो ठीक है, जो पहले वाली थी वो मेटास्टेबल बन गई है, इसका 10-3 सेकेंड है, ये शॉर्ट लिव्ड है तो रेडिएशन लेस ट्रांजिशन है ये। तो यहाँ से एटम यहाँ आएंगे, इतने में दूसरा यहाँ से यहाँ पहुँच जाएगा, और एक सिचुएशन आएगी वहाँ बहुत सारे एटम जो है E2 लेवल के ऊपर आ जाएंगे और E1 में कम हो जाएंगे, इवन हाफ से ज़्यादा जो है इससे ऊपर जाने चाहिए, तभी लेजिंग एक्शन मिलता है हमें। अगर यहाँ हमारे ग्राउंड स्टेट में 10 एटम थे तो 6 एटम जब आपके पास E2 के पास पहुंच जाएंगे तो पॉपुलेशन इन्वर्जन स्टेट स्टार्ट हो जाता है रूबी लेजर में, सॉलिड स्टेट लेजर्स में। और जैसे ही यहाँ से फिर ये नीचे दोबारा ग्राउंड स्टेट आएंगे तो जितनी भी इन्होंने एनर्जी ऑब्जर्व की है इसको लिबरेट करेंगे, लेकिन कोहेरेंट बीम के साथ। तो आपको 6943 6328 एंगस्ट्रॉम का जो है लाइट मिलेगी, जो कि रेड कलर की होती है। सो दिस इज रूबी लेजर वर्किंग प्रिंसिपल, काइंडली नोट इट, right? So in the next step, yes, this is again I have just make this figure more clear that how this is the ruby laser working. Okay, so yes, in few books we have read this thing, but I just make everything clear here, no need. And advantages: ruby laser are economical, construction and function of ruby laser is self explanatory। और इसका डिसएडवांटेज क्या है, वही है कि आउटपुट जो है हमें कंटिन्यूस नहीं मिलता है, और इसमें कई बार डिफेक्ट्स होते हैं, क्रिस्टलाइन इम्परफेक्शंस जो है प्रेजेंट रहती है। सो दीज आर द डिफरेंसेस। ठीक है, नाउ इन द नेक्स्ट स्टेप देयर इज अ गैस लेजर्स। दिस इज नॉट इन योर syllabus kindly, but I just take an overview. This is invented by Ali Jawan and his co-worker at Bell Telephone Lab in USA 1961. Pressure variation, helium is at 1 mm of mercury pressure, and the neon is at 0.1 mm of Hg pressure. And helium used as a lasing gas. Neon is given for to achieve the population inversion state. इलेक्ट्रिकल पंपिंग, वहाँ हम ऑप्टिकल पंपिंग करते थे पिछले वाले में, यहाँ हम इलेक्ट्रिकल पंपिंग करते हैं, इलेक्ट्रिक डिस्चार्ज मेथड इज यूज्ड, एंड इट इज़ अ 4 लेवल लेजर सिस्टम। और रूबी जो था आपका 3 लेवल लेजर सिस्टम था। ये आपने जनरली हमारी फिजिक्स की लैब में आपने देखे होंगे इस तरह से हीलियम नियॉन लेजर जो इस तरह से देखते हैं। सो दिस इज द प्रैक्टिकल डायग्राम फॉर द HENE गैस लेजर्स। ओके, द बेसिक फंडामेंटल इज दिस। ओके, मैं इसमें नहीं जाना चाहता बिकॉज हीलियम नियॉन लेजर इज नॉट योर सिलेबस, बट जस्ट लाइन दैट। ओके, यहाँ देखिए जरा, अब आपके पास एक्टिव मीडियम हीलियम नियॉन गैस का मिक्सचर है। ठीक है, ये आपके पास वही रेजोनेट कैविटी के लिए 2 मिरर है, एक कंप्लीटली 100% रिफ्लेक्टिंग है, द सेकंड में 90 to 98% रिफ्लेक्टिंग। ठीक है, and there is no optical pumping, but there is yes, ये जो आपके पास पावर यहाँ होगा, दिस इज इलेक्ट्रिक डिस्चार्ज। अगर मैं इसको और कंप्लीट करूँगा तो यहाँ मैं हाई टेंशन वोल्टेज से इसको करूँगा, राइट, इसको मैं एनर्जी दूंगा। ठीक है, सो दिस इज द एनर्जी लेवल्स फॉर योर हीलियम एटम, 0 electrovolt to 20.61 electrovolt, excitation by collision with electrons। ओके, क्योंकि जैसे ही आप इलेक्ट्रिक डिस्चार्ज देना शुरू करेंगे, सबसे पहले जो आपका हीलियम है ये एक्साइटेड हो जाएगा, और एक्साइटेड स्टेट में एटम चले गए। नियोन जो है, नियोन ग्राउंड स्टेट में है, लेकिन इन कोलिजन के थ्रू ये जो आपके पास एनर्जी यहाँ आपके हीलियम एटम को है, दैट इज एक्सचेंज टू योर नियोन एटम, and now neon atom also get excited and create their metastable state and having life 10-3 second life period, and after that एट दिस स्टेट 6328 एंगस्ट्रॉम का जो है हमें एक लेज़र बीम मिलता है। और लेज़र बीम मिलने के बाद पर ये कंटिन्यूस मिलता था, पहले हमें पल्स मिलता था, इसमें कंटिन्यूस मिलता है। काली नो दिस, right? This is excitation by collision, then HENE collision starts and there is, yes, देखिए 3.39 माइक्रोमीटर की एक हमें बीम इस तरह से मिलती है, दैट माइक्रोमीटर है, बैरी मतलब थोड़ा माइक्रोवेव रीजन में है। 632.89, दिस इज योर लेजर बीम, and there is one more wavelength, we are getting 1.15 micrometer. These are few characteristics wavelengths we get from this mixture of HENE by making use of electric discharge method in helium neon lasers. Okay, so this is advanced laser, and the actually the power of ruby laser output power, that is much more, but drawback is that is discontinuous. But here the power is less, but it is a continuous. So further, we can say that more and more lasers, different types of lasers that are fabricated by scientists and technocrats by interval, and these are the application of HENE lasers, scientific research, spectroscopy, interferometry, holography, right? GPS system and barcode scanners, laser printers, pointers, and medicine, and dermatology, ophthalmology, laser therapy. These are few very important application of HENE lasers. But now the last and very important laser, that is the semiconductor lasers. Semiconductor, we have, yes, idea. We can say it is type of laser which is somewhat similar to LED, but light emitting diode की तरह है, but LED works on the process of spontaneous emission of radiation, whereas semiconductor laser works on the principle of stimulated emission of radiation. The active medium in such laser is a semiconducting material. Generally we use here gallium arsenide और कैडियम सल्फाइड, जैसे कि एलईडी में हम गैलियम आर्सेनाइड फॉस्फाइड यूज करते हैं, या हम गैलियम आर्सेनाइड या कैडियम सल्फाइड का यूज करते हैं। प्रिंसिपल क्या है इसमें? इन सेमीकंडक्टर मटेरियल व्हेन सम इलेक्ट्रॉन होल रिकम्बाइन, द एक्सेस ऑफ एनर्जी इज आइदर एमिटेड एज हीट एनर्जी और लाइट एनर्जी, and in case of germanium silicon, the emitted energy is in the form of heat, so no use in laser action. Whereas अगर हम जर्मेनियम और सिलिकॉन को यूज करते हैं तो हमें जस्ट एलईडीज की हमें हीट एनर्जी मिलेगी, लाइट एनर्जी मिलेगी। लेकिन हम जर्मेनियम और जर्मेनियम आर्सेनाइड और कैडियम सेनाइड को यूज करते हैं, देन द एनर्जी इज एमिटेड इन द फॉर्म ऑफ लाइट रेडिएशन, एंड यहां से हमें क्या मिलेगा? रेडिएशंस मिलेंगे, and can be great importance in laser action. Yes, only this is the difference. Germanium silicon just light energy or heat energy, but if we are using gallium arsenide or cadmium sulfonide, we get light radiations, and light radiations are there, then lasing action will take place in such type of basic fundamentals. Okay, so now see, a pure semiconductor, we all this is without intrinsic semiconductor है, okay, and the transition of electron top the transition of electrons from top of the valence band, yes, ये transition हम देख रहे हैं, top of the valence band to conduction band. So we can viewed it as generation of electron hole pair, as we know that, okay, and the reverse transition, अगर उल्टा हो जाए, कंडक्शन से नीचे आ जाए, देन वी कैन कॉल दिस प्रोसेस इज इलेक्ट्रॉन होल पेयर रिकम्बिनेशन। पहले इलेक्ट्रॉन होल पेयर बनता है, अगर रिवर्स हो जाए तो इलेक्ट्रॉन होल पेयर रिकम्बिनेशन होता है। ओके, सो नाउ सी, पहले आपने क्या किया, ये देखिए जरा, फोटोन जो है, फोटोन्स दैट इज इंसिडेंट ऑन द सेमीकंडक्टर मटेरियल गैलियम आर्सेनाइड, and here in the valence band, okay, the few valence band, the atom observe the, if I say one atom observe this photon and goes to the higher state, that is the conduction band. Okay, this is just like a stimulated absorption, and after that, after the conduction band, it, yes, and in the particular state, if you give the more photon, अगर यही है, if you again external photon is given to the system, what happen, यहाँ से ऊपर तो state है नहीं, because it is a semiconductor. Now it goes to the valence band by liberating the two photons now. One is primary photon along with the secondary photon, and both electrons are in phase. Just this is the, you know, basic how we can say the lasing action takes place in the semiconductor. This is the basic diagram. Okay, and the band, the semiconductor material is illuminated the photons whose energy is equal to or higher than the band gap, then photon can be observed. Okay, ये मैंने आपको clear कर दिया है. Same I am saying, yes, I have cleared this all to you. I have cleared this all to you. Okay, and okay, ये I have cleared all to you. Now when now I just see the lasing action in pure semiconductors. Yes, we are getting the lasing action, but just providing the external photon to the system when your atom that is already in the excited state. Okay, the excited state that is in a conduction band, right? So now I am using the N-type semiconductor. N-type semiconductor, that is when a pure semiconductor that is doped with pentavalent impurity. Pentavalent impurity like your arsenic, antimony, phosphorus. The resulting material is so formed is known as N-type semiconductors. Okay, having more electrons, free electrons, valence electrons. When pure semiconductor is doped with trivalent, we are getting the P-type. I forget to write P-type semiconductor is there. Okay, trivalent and pentavalent impurity. Okay, the donor energy level is just below the bottom of the conduction band and having energy 0.01. Yes, in this case, when I am dealing with the N-type semiconductor, then this particular level is known as the donor energy level, this level, and this is having energy 0.01 electrovolt just below the conduction band. It means the free electrons are here. Now, what you do? Again, you give the external photon to the system. When you give the external photon to the system, these free electrons, they are goes to the conduction band and leaving behind the holes here. Okay, leaving behind the holes here. This is the case. When the temperature, yes, when the temperature of N-type semiconductor is gradually increased from 0 Kelvin, this process is at 0 Kelvin. But when you heat the system from 20 Kelvin to 50 Kelvin temperature, right, then transition of electron from donor energy level to conduction takes place. This process is at particular temperature after 20 Kelvin temperature. Okay. Around 20 to 50 Kelvin, the donor energy level will be depleted. All the donor electrons have donated their electron to conduction band. This makes the material N-type degenerate. That is what we are able to get the population inversion state at this step. If there is population inversion state, we get the laser light. This is the basic lasing action in N-type semiconductor. Okay, let's take the example of P-type. This is again, I mentioned the same diagram, P-type semiconductor. Okay, now in P-type, this is the accepted energy level, and accepted energy level is just above the valence band because ये तो fully filled band है. The energy is delta is 0.01 electrovolt. Now that is at a 0 Kelvin temperature. The scenario is this. There are the free electrons are this. Okay. This is the band gap. This is the actual band gap. Okay. This is the conduction band. Now what happened? You just increase the temperature from 20 Kelvin to 50 Kelvin temperature. Then there is a transition takes place. I represent this by this arrow. Transition takes place, and your electrons they raise to the level towards the valence band and leaving behind the holes. And this again makes the material p-type degenerate. That is, we are able to produce the population inverter state here. If once we get the population inverter state, there is lasing action that's occur. So this is the basic lasing action in semiconductors. It's very, very important to understand, right? Okay. Then in the real because our lecture is in material science, then kindly note this. We have to make the injection laser, that is a practical laser of semiconductor, then what I have. The structure of injection laser is similar to that of LED. Yes, okay. LED works on the principle of spontaneous emission, whereas injection laser works on the principle of stimulated emission of radiation. It consists of having depletion junction diode and a large concentration of electrons, the whole necessary for production of power. Okay. The PN junction used in the form of rectangle wafer. Yes, we are going to see in the next slide. It is 1 millimeter, 1 by 1 millimeter, 20 micrometer. That's the standard size, because it is very, very small in size. The front and backward sides are polished parallel to each other, to make the resonator cavity. The other two faces are made rough to suppress the oscillations in the unwanted directions. Okay. The PN junction is kept at forward wise using external battery source. These are the few basic fundamental that should be in our mind to fabricate the injection laser. Okay. So this is the one of the best figure I have made to understand this. Okay. So this is your, from this to this, it is your p-type semiconductor. It is sandwiched with n-type semiconductor, and the junction that is in yellow in color, it is the depletion region. The dimension of this silicon wafer, that is 1 millimeter, that is 1 millimeter, that is width, right? 1 millimeter its height, and 20 micrometer its we can say 1 millimeter length, 1 millimeter breadth, and 20 micrometer its height. Only small like this. Now, and these two faces, face 1, face 2, these are rough surfaces. Why to made rough? To suppress the oscillations of light in other directions. Second, phase 1 and phase 2. Yes, this is phase 3 and phase 4. These are coated reflector. These are the reflectors. 100% reflector. Phase 4, this one. Phase 3, 90% reflector. That forms the resonant cavity. These are the electrodes to make it forward wise. To make it, this is the P type. It should be linked to the P terminal of the battery. This is N type. It should be linked to N type to make the system forward wise. And your this is the highly doping is taken for to make this injection lasers. So what the advantage is? This type of lasers are highly efficient than other type of lasers. 70 to 80% efficiency, but by making of other we just have the 20% efficiency only. These are used to construct quantum amplifiers because of high sensitivity. These lasers integrate with FET BJTs to form the optoelectronic circuits. These these lasers consume low power to operate. And construction is very simple, not very high. It is very simple construction is there. So these are the advantages. What are the disadvantages? Disadvantages, yes, depend on temperature effect. Okay, beam divergence is much greater. It is 125 to 400 milliradian. That is directionally is low. Not used in complex or typical laser application. Not used for industry like welding and cutting. For welding, there is CO2 lasers. They are used, and there is another one. There is ND doped YAG lasers. Other types of lasers. They are used, but for electronic part, it is one of the best lasers that has been fabricated by the technocrats. So thanks a ton. Thank you very much. Any question, any query, you can ask in my class lecture. Thank you very much.